Good morning, everyone. Welcome to this poster lightning talk session. This year we are expecting 54 posters, and of course we can't feature them all here. So we made a selection of 14 student posters that we would like to show to you to interest you in our wonderful poster session this afternoon. So the thing that is most important for you to remember, 5:30, CW building, and there will be beers. So this session is going to work as follows. We have 14 students. I will call them on stage. They will have a 2-minute presentation, and then they will move on to the next. Next one will go on stage, will be introduced. And then at the end, I will come up with some housekeeping announcements. Now, when I asked everyone to give me a slide, of course, being students, they try to bend the rules. So you might see a lot of animation that you would wonder, isn't it actually 8 slides? But we go through that. That's fine. They are in a very particular order. They're in order that they got sent to me. So if you're handing in a slide 1 week in advance, you're probably quite up in the front. If you hand in a slide 20 minutes before this session started, then you are likely to be at the end. So without further ado, I would like to announce the first student poster lightning speaker, which is Mahmoud. Please welcome Mahmoud.
Good afternoon, everyone. My name is Mahmoud, and I'm from the University of Southampton, and I'm presenting our latest research on enabling flexible Internet of Things devices. And today is going to be a tale of 2 challenges, wireless connectivity and power. Anyone who has done IoT has seen these before, commercial wireless modules that you just plug in your system and your wireless connectivity problems are magically sorted, but this has never been a wearable-friendly solution. We are presenting an entirely flexible wireless module that is ultra lightweight and low cost and has superior electrical characteristics to conventional PCBs. And when it comes to applications where you cannot compromise on radio performance, you should never settle for a reference antenna. We are proposing a novel 2.4 gigahertz antenna that has up to 10 dB higher on-body gain compared to commercial industry standard reference design. In other words, by using our antenna, your radio waves get to travel at least 3 times further distance. Moving on to the second challenge, which is power, a wearable device has to be long-lasting, a fit-and-forget solution, and batteries fail to meet this criteria. We are proposing an entirely flexible power supply module from different energy harvesters for different use cases, so rectifiers and supercapacitors, all realized entirely on textile or flexible materials. And since we're doing this case study in the insole, we're using a ferroelectric energy harvester, which harvests step force in the form of voltage spikes. And even though you can see it's producing fairly high power output, it comes with very high source impedance. However, with smart switching-based power management, we use it to entirely power up a Cortex-M, a wireless ARM SoC, in under 5 to 7 steps, performing 3 ADC samples and 1 Bluetooth transmission, all from the 48 MHz Cortex-M3 on a commercial SoC. So summarizing this up, I'm presenting to you today the world's very first entirely flexible sensor node that is self-powered and has a high-gain RF front end that is bespokely designed for wearable applications. That's it. Thank you. I'd like to introduce Cecilia.
Hello, I need to change my slide first. There we go. So hi everyone, I'm very excited to share a bit of my research with audiences from engineering field. I'm a second-year PhD candidate in service design from the Royal College of Arts in London. Since several years ago, I've been researching about user experience problems such as the lack of user engagement and user abandonment in smart service sector. And we've seen a significant user dropout rate in both consumer wearables and mobile app spaces so far. If you look at these days, as AI is fast permeating into every aspect of our lives, I think that it's important for the design community to really think about how we as designers can augment the positive impact of AI. A lot of developers these days talk about how we can build emotionally intelligent gadgets, but building emotionally intelligent gadget does not necessarily mean that users will find that interactive experience more engaging and emotionally rich. So to the end, in my research, I'm trying to articulate this gap through exploring what are the experiential design elements we can utilize to elicit the most contextually appropriate emotional response in users. And to the end, I'm looking at olfactory sense, which is directly linked to the area of the brain that controls human emotions. So if you are interested in learning more about how we can use smell to design for emotionally engaging interactive experience between human and machine, come and find me later at the poster booth. Thank you. I would like to introduce my next speaker, Adrian.
Oh, sorry, let me just change because, right, where's the other post-it? Right, the one here. Yep. Cool. Good afternoon, everyone. So my name is Andres, and I'm a PhD student at the University of Bristol. So the aim of our project is to utilize the hardware garbage collection to support managed languages in resource-constrained devices, which often have very tight timing requirements. So garbage collection is obviously widely used already in software development as it improves programmer productivity and also reduces the likelihood of errors. However, the majority of collectors have very high performance, have very high overheads in general. So they are not very suitable for the kind of embedded and real-time systems we're targeting. For example, some collectors utilize 50% of the processor utilization of the processor capacity, so that's not very useful. Also, the majority of collectors are not suitable for any kind of real-time analysis, or if they do, they are very difficult to use. So we're proposing a new memory architecture that is called Scharth, which has a hardware memory compact collector embedded in the processor itself, which continuously reclaims the memory in spare memory cycles. The ideas behind Scharth are completely independent of the underlying instruction set architecture, so we can use it with something like ARM or RISC-V. And we've, in fact, we've already integrated it with a Cortex-M processor, and we're running some workloads such as a MicroPython interpreter. In this case, we observe performance improvements ranging between 20 and 80%. So the main focus of our design is actually trustworthiness via simplicity and verification, whilst maintaining optimal performance. So we've already constructed a timing model of our design and to support dynamic memory in hard real-time systems, and we're working to validate it. We're also working to formally verify our design, and who knows, maybe it's time to say goodbye malloc and free. So please pop up by our poster. Thank you. So our next speaker will be Amna.
So, hello everyone, I'm Amna, and I'm a PhD student at the University of Edinburgh. My research focuses on memory subsystem design for data center servers. The explosive growth in dataset sizes is imposing skyrocketing processing demands on data centers. Meanwhile, the performance gains achieved through technology scalings are nearing an end. Now, in order to extract higher performance, we need to rethink server processor design. State-of-the-art server processors dedicate more than a third of the chip area to last-level caches, or LLCs. The LLC is shared between the cores to maximize effective capacity. This shared on-chip LLC architecture has a number of limitations. First, on-chip area constraints limit the capacity that can be provided. Second, long interconnect spans increase the LLC access latency. Third, the shared LLC capacity faces contention under workload collocation. At the same time, the server applications have the following LLC requirements. They require large LLC capacities to capture the growing data sets. They require fast LLC accesses because of low memory level parallelism in the application. Finally, server applications, when co-located, require performance isolation. We find that the existing LLC configuration is not suited to the requirements of server applications. In this work, we propose a private die-stacked DRAM cache architecture, referred to as private die-stacked LLC organization, which directly addresses the needs of several processors. Please stop by during the poster session for more details. Thank you. And next speaker will be Grigorios.
Thank you, everybody. Good morning. I'm here to introduce you a brain-machine interface that it's built around the heterogeneous SoC. We are using a skew system to create our brain-machine interface, and we actually developed several custom IPs that we put inside our fabric logic. These custom IPs are specifically designed for EEG data processing. As you can see, we have managed to create several EEG IP blocks for signal filtering, denoising, artifact injection. And the whole thing is based on the two events that are happened during human motor imagery movements, the ERD and the ERS effects. And for the first time, we are introducing inside our fabric logic an ARM Cortex M0 from design start. We are using this kind of processor to supervise the whole EEG data processing. And of course, the processing system, we have a processing system that captures the EEG data from a portable EEG data set, EEG device. And then we use custom IP blocks to control movement rehabilitation devices. If you got any further questions, I will be at the poster session. Thank you very much for your time. Please welcome Pablo.
Hello, everyone. I'm Pablo Hernández from University of Zaragoza. What did I do? All right. So we focus our work on one of the major constraints in current chip design, which is the temperature dissipation. So to do so, we combine computer architecture, control engineering, and a bit of thermodynamic knowledge to apply a more formal control to the thermal and frequency control. So we use a transfer function mathematical model in order to characterize how the changes in frequency affects the temperature of the chip. With this model, we design and tune a PID controller, which is then implemented under the Linux kernel governor. This differs from the current approach that use more complex heuristics. And for the test, we use a tunable matrix multiplication benchmark, which is an example of a constant workload. We successfully managed to keep a constant temperature in the chip without reaching any thermal alarms, which lead us to less frequency changes, which also lead us to improvement in the performance. Right now, we are working on a variable load adaptive estimation from the PID parameters and support from any device on the system on chip. I'll be happy to talk with you in the interactive session and ask you and answer your questions. And now, Priyanka, sorry.
Thank you, Pablo.
Okay.
Hello, everyone. I'm Priyank from the University of Edinburgh. I'm going to make a case for domain-specialized cache management for graph analytics. It is a well-known problem that graph analytics exhibit poor cache efficiency. However, what is surprising is that it is true even for graphs that have high skew in the vertex connectivity. Skew is a blessing in disguise for cache efficiency. The skew in the vertex connectivity leads to a phenomenon that we refer to as hot vertices and cold vertices. Hot vertices are only a tiny fraction of the total. They dominate overall connectivity and leads to very high reuse. So hot vertices are perfect for caching, require small capacity, incurs high reuse. Cold vertices, however, are very large in numbers. And by definition, they have low connectivity, which leads to very low reuse. At cache level, cold vertices occupy capacity with hot vertices, which causes thrashing. So to hardware, all vertices look similar. The bottom line is, existing hardware-only schemes struggle in correctly identifying hot vertices. So how do we propose correctly identifying hot vertices in hardware? Refreshingly, we don't use neural network to do this. Instead, we apply a very simple yet elegant software-hardware co-design to do this. The software component segregates hot vertices simply based on their degree. The hardware component employs cache management policies to protect hot vertices from thrashing. The net result is high cache efficiency in graph analytics. If you want to know more about the design, please look out for the poster number 22 in the poster session. Thank you. And let me welcome the next presenter, Banav Saj.
Hello, everyone. My name is Banav Saj. I'm from Newcastle University. Today, I'm going to present ultrasound wireless implantable for fluorescence sensing. My implant size is 12 by 5 millimeter, and the targeted power consumption in microwatt range. This is why I'm using Cortex M0 Plus. My implantable device is able for optically stimulating the cells at 470 nanometers, and also optically records the release from genetically encoded calcium indicators, just like GCAM6. The recorded data will be transmitted through the tissue into external part using PZT ultrasound transducers. These transducers are implemented from scratch. The operating frequency for these transducers is 300 kilohertz. For more details about this work, please visit me during the poster session. Thank you for listening. Now let me introduce Tim to present his work.
Okay, my name's Tim Dolby. I'm a student at the University of Southampton. We heard from Stuart this morning how the Internet of Things is a scale from devices with rich capability to really ultra-constrained devices. And it's these ultra-constrained devices that's the area I work in. One of the biggest, many people use batteries, but these obviously have a big downside in that they require replacement, which is a high maintenance cost. And so that leads us to look at things like energy harvesting. But even supercapacitors and rechargeable batteries increase the size, mass, and cost of the system. So at the University of Southampton, we look at how we can completely remove this energy storage and operate only when the supply is available. And the way that we sustain computation across multiple power cycles is by checkpointing the system state, so that's registers and RAM, and saving that into a non-volatile memory. this work, Hibernus, sets up voltage thresholds to detect when that supply is about to fail in order that it can do a hibernate, and then another voltage threshold where it is able to restore. And my work increases the forward progress of Hibernus by limiting the number of checkpoints that we do. Checkpoints do incur a high energy cost and a high time cost. So the more of those that we can remove, the better for our forward progress. And so I introduced power napping. Maybe my bias is influenced by being a student that likes sleep. But that's how, come and ask me more about how that works at the poster session. I'd now like to introduce Chow, our next speaker.
Hello, everyone. My name is Zhao. I'm from Loughborough University. Today, I will introduce 4 applications of deep learning in image processing. Over the last decade, the ability of computer programs to extract information from images has increased tremendously. We owe most of this advancement to convolutional neural network. We also call it CNN, which is a typical neural network specifically for processing the image data. The first application I want to talk about is image denoising, which is to reserve the details of an image and at the same time to remove all the random noise. The second one is the color correction, which specifically for the darkening and toning down the exposed images. The third is image demosaicing, which is to reconstruct the full color image from the incomplete color sample output from an image sensor overlaid with the color filter array. The last one is super resolution, which is the process where our input is the low resolution and coarse image, and our output is the same image but with more detailed and in high resolution. If you're interested in my topic, please check out my poster. My poster number is 11. Thank you. The next speaker is Yasser.
Hello, everyone. My name is Yasser. I'm a research student at the University of St. Andrews. So my goal from this research is to find a way to predict energy consumption in parallel functional programs, specifically in Haskell. So the idea is that we want to look at a high-level language such as Haskell, where we have specific features such as purity and characteristics of evaluation expressions. Also, we want to have a high-level way of looking at the energy consumption from a high-level point of view. So in this case, we look at the runtime metrics, that is being the mutation and garbage collection. For example, looking at the graph on the right side, we look at an example of Euler summation algorithm, which is part of the standard benchmarking suite from GHC. So the example on the right hand side shows a consistent speed-ups for this algorithm with an opposite approach, an opposite energy consumption on the other hand side. I'm happy to further elaborate on this. My poster number is 20, and now with Siddharth.
Hello, everyone. I'm Scharth Mahwa. I'm a PhD student in Newcastle University. And through my poster, I want to ask a question, whether we can bring genomics on a smartphone. So what is genomics? Genomics is a study of genome. And genomics, the most important application of genomics is medicine. There are more than 6,000 genetic disorders in medicine. Medicine today is undergoing transformation from reactive to personalized, predictive, participatory, and preventive form of medicine, which is P4. But with this over 6,000 genetic disorders, genomics is the front runner of this transformation. And all this research and development and the development of therapy and prognosis of genetic disorders are currently largely taking place in data centers. With data centers, which is employing very powerful many-core processors, employing GPUs for acceleration, genomics is also poised to become the largest data producer by 2025. So we need to solve this problem because there is high energy consumption, there is huge electricity bills, and there are many limitations and disadvantages with data centers. What we want is we want to bring this genomics to mobile devices, handheld off-the-shelf mobile devices, which is very synonymous to Wikipedia, where the storage is centralized, but the distribution of labor, everyone around the world can contribute to this database. Similarly, through our work, we are proposing this tool, which is a OpenCL-based genome assembler, to assemble the genome in an embedded platform. And from this, we will go forward towards bringing genome analysis also on an embedded platform, and thus we envisage building a complete genomic system, which like ECG system, which is employed nowadays in all the hospitals. So bringing genomics to the end user, which is each and every human being. If anybody is interested in bioinformatics, genomics, big data, or embedded processing, please come and have a discussion with me during poster session. Thank you. I would like to introduce the next speaker, Michele.
Okay. Good morning, everybody. I am Michele Zanella. I am working on at the IPLab group of Politecnico di Milano. And we are currently working on and study on how to extend the resource management in mobile devices. We are working on a barbecue runtime resource manager, and we are extending it with a sort of API and some wrapper from the native side of the resource manager toward the Java environment. This API exposes an adaptive execution model so that the application can negotiate the performance request toward the system. In this way, we can perform a two-way resource management. First of all, at system level. So, for example, taking into account energy efficiency and, for example, isolation. And at the application level, taking into account, for example, performance. In this way, application can develop in order to allow the user or self-aware application to ask for more or less performance and thus more or less power. Finally, the runtime resource manager will allocate different resources through a set of mechanisms, for example, like CPU frac for frequency scaling and so on. If you are interested in further details, we are looking forward to see you at the poster session. Number is 34. Thank you, and I'd like to introduce you, Adrian.
Hi, I'm Adrian from Newcastle University, and I'm presenting a poster entitled Faster and Cheaper Circuits Through Self-Timing. I'm promoting asynchronous logic design, where we say the computation's done when it's done, and we're not going to wait for any clocks, rising clock edges. And by doing this, we can achieve better performance and better energy in some cases. My work specifically targets low-power devices, and yeah, come and find me and talk about asynchronous design. And my work specifically is
on simplifying the completion detection for those of you who might have some knowledge of asynchronous design already. So that concludes our lightning talks. So now I can hand it back over to Renee.
Okay, thanks to our speakers. I really loved the variety of this year's poster session, so please do come along. For something slightly different, since 2002 there's a concept art traveling around the world by Yayoi Kusuma, which starts out as a blank white room with nothing in it. And then people entering this room get a sheet with stickers, and they can place it anywhere where they like. Now, I know exactly what you're thinking at this point. This sounds like an ideal way to determine who is this year's best poster. Upon entering the CW building, you will get 5 stickers. Each poster will have a appreciation token sheet, as I think we call it. You can distribute these stickers however you like. You can place 5 with one poster. You can do 1 on each poster. It doesn't matter. If you like a particular poster presenter, the way that they talk, the way they present themselves, if you like a particular poster, the content or the way it's designed, maybe you like a particular graph, all these are valid reasons to give a sticker. Most stickers wins, as simple as that. ARM employees that have a poster are exempt from winning the award. They are not exempt from receiving stickers, so please spread some appreciation to them as well. And with that, I conclude this lightning session. I have 2 household announcements. One is we have received a poster via the mail, which we're going to hang. It's called An Ideal Root of Trust Solution Integrating Physical and Clonable Functions. And then I can't read it further, but if this is your poster, please come and find me in the CW building, because we would love to put you on the floor plan with the proper name of the presenter as well. If you're one of the 20 posters that have not handed in their poster yet, please do so in the next break. We will all hang them for you. You will get a number, you will get a location, everything will be sorted out, but to make sure that this process is as fluent as it can be, we would like to have the poster up front. So please all come. 5:30, CW building, there will be drinks. See you all there.